Hi, I'm Dave Burley. I'm a physics instructor here at the University of Maryland, and this is the potential well or the hill track model. So I have a question for you. I'm going to take this 3-ball, and I'm wondering whether or not if I release the 3-ball from about the same height on the track as the height of the hill, will it make it to the top of the hill? Okay, so it doesn't seem to make it the whole way. Why is that? Because we certainly have talked about in our energy conservation relationships, particularly mechanical energy, that if we have an object that is starting from a certain height, it'll have a certain amount of gravitational potential energy. And of course, by the time the billiard ball reaches this height, it should also have the same gravitational potential energy. So what we expect is that as the ball goes down the ramp, it's losing gravitational potential energy and gaining kinetic energy. And of course, once it goes back up the ramp, it's losing that kinetic energy and of course is being transformed into gravitational potential energy again. So what's the problem? Why is it that when I release it from the height that I would expect for it to make it to this position, it doesn't quite do it? Well, there are two pieces that we kind of have to think about, and they both involve what's going on with the fact that my ball is not just sliding down this ramp, it's actually rolling down the ramp, which means when I'm looking at it, there are actually two different kinds of kinetic energy that are being that potential energy is transforming into. One of them is the one we're used to, what we call translational kinetic energy. It's 1/2 times the mass times the speed squared. The other one is rotational kinetic energy, and that's what happens when we talk about a real object that is rigid and is going to have a very specific shape and distribution of its mass. It'll have what we call a rotational inertia or moment of inertia, and as it's doing that, that means that some of this gravitational potential energy as it's falling is indeed being transformed into translational kinetic energy. But it's also being transformed into rotational kinetic energy, which means that the object is going to roll as it's falling down. And when you might have noticed that even when it reaches that highest point, it's still spinning a little bit. We also have a little bit of loss. The fact that it's rolling tells us that there's another force that we have to consider in real circumstances, and that's friction. Friction does not play by the same rules as our conservation of mechanical energy does. It is not a conservative force, which means that it's not going to be something that has a potential energy associated with it. And in this case in particular, it's a form of loss. So when I release from this height, the ball doesn't make it because some of the energy that it had at this highest point was lost to the system due to friction. Work was done by the ball onto the track. And if we watch it carefully and just let it go on before grabbing it, you can see that every time the ball goes by, a little bit more of that energy has been transformed by work into lost or unavailable energy. So even though we might still say that the law of energy conservation is valid, if we don't include the work that was done by friction on this object, we're missing out.